All right, guys. It is AP test prep level 1C. Okay. Uh, kind of piggybacking off the last video, we're gonna talk real quick about substances, calculations of purity, and then we're going to talk about the atom and electrons. Okay, so firstly, we've got substances. Okay, you can have a pure substance, a mixture, and of these two, they can contain compounds or elements. Okay, so a pure substance would be a container that only has one type of particle in there. Okay, this would be a pure substance of unfilled purple circles. Okay, we could also have a pure substance of whatever that is. Okay, I would call that two filled and one unfilled circle bound together. Okay, while there are two different types of atoms present in the container, it is still only one bound particle. So each one of these is a particle, and so it is one type of substance inside the container, and so it is by itself a pure substance. Okay, or you could have a mixture, okay, where you have some open purple circles and some of these. Okay, so it's two different entities inside one container. Okay, difference between a pure substance and a mixture. Now, difference between compounds and elements. Compounds, obviously, are two different atoms or circles, in this case, bound together to form one particle. Okay, that is two different elements bound together to form one particle. Okay, now an element would be either just the singular atom or a series of that atom bound together. Okay, I'm thinking about like a solid block of copper. Okay, it's purely copper metal. They are bound together, but they are solely the copper metal, and so that would be a denotion of an element. Okay, you can also have diatomic elements, something like hydrogen. Okay, H2, that is a diatomic element. Even though it comes in pairs like that, that would be a diatomic element. Okay, so you can have a pure substance of elements, or you can have a pure substance of elements, or a pure substance of compounds. You could have a mixture of elements and compounds. Or any sort of combination of the two. Okay? So that's the types of substances. Now, calculations of purity, we can talk about percent mass, So if we have a 10-gram sample of table salt, and then we dissolve it and find that there were impurities, we can take that into account and say let's say there were 2 grams of impurities. We can take that into account and say 8 grams of actual salt were present in that 10-gram solution. And so we have an 80% salt mixture. Okay, so that would be a type of percent mass purity calculation that you might see. Okay, now lastly, and the most important part of this is talking about atoms and electrons. Okay, now atoms, they went through a couple different historical models. The first one being Dalton's, where he said, you know what, it is just a sphere that cannot be broken down. And all spheres of the same type are identical. So a sphere of, say, that's hydrogen would be always the same as another sphere of hydrogen. Okay, it would never, you'd never have one hydrogen different from the other. Now Dalton, I'll write that out. This is Dalton. Dalton was right in saying that these spheres make up everything, that they can be thought of as sort of spherical, and that most 90% of the time these spheres are identical to each other. However, they are not always identical, and they can be broken down. Okay. So next up, I believe it was Thomson. I think it was Thomson. Next, and he had the plum pudding model. Okay, where you had a atom, and there were bits of negative charge in there, which he called electrons. So the electrons are just placed inside, and then all the blue area here in between these dots is the positive charge of the atom. Okay, he did this through a cathode ray. So this ray is a negative charge, and then he put magnets on one or both sides and saw that it deflected one direction. And so he was able to find the existence of electrons and knew that they had to be put into the atom. And so he came up with the plum pudding model. Okay, obviously that is not exactly correct. The positive charge is not just condensed or is not just throughout the atom. It is condensed, and that's where Rutherford came in. Rutherford found the nucleus and atoms are mostly empty. Okay, so he had the gold foil. He put a thing of gold foil, very, very thin, in a container that had a film around it, and then he fired alpha particles at the gold foil. Now, if it was anything like the plum pudding model, you'd expect the majority of them to bounce back or just go straight through. Okay. However, he saw that some were deflected and to the side, and some bounced straight back. So that tells us that the positive charge is condensed in the middle, and if some particles pass through, and since particles pass through, the atom is mostly empty. Okay, and so his model looked something like a condensed nucleus and electrons surrounding it. Okay. Last one I want to talk about is Bohr. He found when electricity is pumped through hydrogen gas, a spectrum of specific colors were found. Okay, so the specific part is important. This tells us that the electrons are in specific energy levels. Okay, if they were not specific colors and just like a spectrum of the rainbow, so when I say specific colors, I'm saying he looked at the spectrum and he saw a line of blue, maybe a line of like purple, and then like a line of like green or something. It wasn't just blue continuously up to here, and then it shifted into some purple and then some red, stuff like that. No, he's found specific lines. This tells us that there are specific energy levels that correlate to each color. Okay, so that these electrons, when they get excited by the electricity, go up to a higher energy level, and then they go back down and they release light. Okay, and that light has a very specific energy to it because of the jump that the electron made. So that told us about the specific energy levels that atoms have. Nowadays, we find that the atom is a nucleus with electrons surrounding in a cloud of probability, and that probability follows specific orbitals. Okay. Now, those specific orbitals can be found in our periodic table. Draw that. And finally there. Okay. And then the lanthanides and actinides. Okay. So these specific orbitals are shown as the s orbitals, the d orbitals, the p orbitals, and the f orbitals. Okay, SPDF. Also, these orbitals have specific energy levels, and they go by the period of the periodic table. So 1, 2, 3, 4, 5, 6, and so on. Okay? So, each electron in an atom follows the periodic table in electron configuration. Okay, so hydrogen right here, it is in the first energy level, and its electron is in the s orbital. Okay, and so the electron configuration for hydrogen would be 1s1. Okay, it only has one electron. That's where this one comes in. It only has one electron. It is in the s orbital, and that s orbital and that electron are in the first energy level. Okay, so the electron configuration for hydrogen would be 1s1. Okay, now the biggest point that we can say is that these electrons follow, it's called Aufbau's, I think I'm spelling it wrong, but Aufbau's principle. Aufbau's principle says that electrons fill the lower energy levels first, then go higher. Then you have Hund's rule, which says electrons, if they have open equal energy levels, they will fill those first. And the Pauli exclusion principle it says that if two electrons are in the same orbital, then they must have different spins. Now, all these rules I will make apparent in this next example. So let's take the example of carbon, an easy one. Not easy to write, apparently. Carbon. Okay, C. It starts with its electrons in the first energy level, which makes elements or electrons 1 and 2 are in an s orbital, and there are 2 electrons there, so it's 1s2. Then we go to the next closest orbital. If we look at the periodic table, that is in period 2, and that is also an s, okay, which means there's also 2 electrons in there as well. Then we can go into the p orbitals, so 2p, and then carbon has 4 electrons in that p orbital, so it's 2p4. Now, if we were to draw these electrons, not necessarily draw them, but write the arrows for them, we would have, and ooh, that's a bad line, I don't like that. We'd have in the first orbital, we'd have 1 electron going spin up, and the other one spin down. And that's the max amount of electrons that are in the s orbital. Same for the second one. And then the p orbital, it can have 6, which means it can have 3 groups of 2. Okay, it can have 6 electrons in there, which is 3 groups of 2. Okay, and so we are going to fill up each equal orbital first. So it has 4 electrons in this orbital, so we have to fill up all 3 with 1, and then we have 1 left over, so we're going to go and put 1 spin down into another, into the first orbital here. Okay, now there's a lot of reasons for why there's 1 orbital for s and 3 different ones for p. That is all getting into some physical chemistry stuff, which is my favorite class, but not for you guys. So this stuff is what you guys need to be able to do. Now, some of you guys might be saying, what about quantum numbers? Not super important, okay? What you can remember is that there's a quantum number n, then L, then M sub L, and then M sub S. Okay? N is the energy level, or the period. Okay? L is the type of orbital, whether it's an S or a P, or a D or an F. So S, P, D, or F. M sub L tells you which one of the suborbitals it is in. And then M sub S would tell you whether it's spin up or spin down. Okay, so those are the quantum numbers. You do not need to know those for the, like you don't need to be able to assign them to an electron for the AP test. Okay, now I'm going to do one more example of electron configuration, and I'm going to do an element that is in the d orbital, okay, because some wonky stuff kind of starts to happen there. So let's do cobalt. Okay, CO. And for this, I'm going to actually have to pull up a periodic table. All right, it might help for you to also bring up a periodic table, so go ahead and do that. Pause the video if you need to. But we're looking at cobalt. Now, cobalt is in the, what is that? The 9th group. It is a transition metal, and it has 27 electrons. Okay, now, it has 27 electrons. Its 27th electron would be its last, but everything leading up to that will be its core electrons. And so it follows the same pattern that we saw up here. So we can go ahead and get started because it has all of these electrons. It's 1s2, 2s2, then a 2p6, then a 3s2, and now here's where we get into some shifty area. Okay, or sorry, not yet. 3s2, 3p6, and then now is here we're getting to some shady area. The next one would be 4s2. Okay, remember these large numbers are the energy levels or the periods, so we're down into the 4th period now. We're 2 electrons into the 4th period, and now we get into our transition metals, which is the d orbital. Now when you get into the d orbital, you have to change the energy level. Okay, so d orbital electrons are not in the same energy level as the ones before it. They are very high in energy, so they are very close to the energy level of 4, but they are not in the 4th energy level. And so it is 3D, 3D, and there are 7 electrons, or no, not 7, yeah, 1, 2, oh shoot, where is it? I lost my periodic table. 1, 2, 3, 4, 5, 6. Yes, 7 electrons in the d orbital here. So 3d7. Okay. Now, this is the important part. When you get into the d orbital, it is always 1 less than the s orbital before it. Okay, the energy level of it. Okay, and then if you get into the f orbital, it would be 2f. Okay, the f orbitals are even 1, well, it wouldn't be 2f for the, in real life, but it would be 1 less than the d orbital then. So say we are at d orbital, it would be d orbital 5 is where the first f orbital shows up. So 5d, and the f orbital then would be 4f. Okay, so keep that in mind when you're doing your electron configurations. Now, if we do our drawing of electrons, it's going to be a lot of them. We do 1s2, and then 2s2, 2p6, 3s2, 3p6, 4s2, 1, 2, no, not 2 there. 4s2 would be 1, 2 that way. And then 3d7. Now the d orbital can have 10 electrons, and so there are 5 pairs of 2. Ooh, almost ran out of room there. There are 7 electrons, so we go 1, 2, 3, 4, 5, 6, and then 7. And there you go. There is the electron configuration of cobalt. Okay. All right. Now that is a 30-minute video, the longest video I've ever made, but it covered a lot of material, a lot of important material. Okay. So watch this, comment if you have any questions, email me if you have any questions. and go from there. Best of luck studying to you all.